exploiting Vibronic couplings in Rydberg ions and atoms from mediated physics.
No, I'm getting it. Yeah, you may need glasses. Okay, yes. So thank you very much, Thomas and Michael, for inviting me to this nice conference. Maybe just a few things for a start. So I moved institution recently. I'm now at the University of Tübingen, so the program says I'm still in Nottingham, but since 6 weeks ago I changed institution. The title is, I don't know whether you like it or you find it appropriate. It was kind of an attempt to marry what I'm talking about with somehow molecular physics. I don't know whether this worked well, but it's up to you to judge, and you will tell me towards the end. So what I'm going to talk is about exploiting Vibronic coupling in Rydberg ions and atoms for many-body physics. So as I said, I'm currently at Tübingen setting up the group, so a number of people that are there will start very soon, still looking for PhD students. But what I'm going to talk about is in fact to a large extent, the result of a bigger collaboration involving, of course, people in Nottingham, Waben and Filippo, but also co-workers at Mainz, in Ferdinand Schmidt-Kahler's group, and most importantly, Marcus Henrich's group in Stockholm. And if I'm entirely honest with you, this whole talk makes me more feel like doing the support act for something that you should really be looking forward to, namely your talk on, I think, Wednesday morning, right? Okay, so I'm trying not to reveal too much, but to keep the tension rising somehow. Okay, so this is the outline of my talk. I start by talking briefly about trapped ions and Rydberg states. Why would we want to do that? That's maybe the first question. What are the challenges? What are the properties, good properties of trapped Rydberg ions? And then you will show rather naturally, we'll bring in somehow this notion of Vibronic couplings and sort of resemblance to molecules, which we actually have also seen in Hartmut's talk to some extent. And also, the thing is that this topic, maybe this is something I also wanted to say, because it ties me also to some extent to the chairman. I don't know whether you remember, so we started on this when I was still a postdoc in Peter Zoller's group in 2008, and we had also you with Pete Schmidt, right, and Marcus Müller, we had lots of discussions about this, so you will see in the end this kind of worked, so surprisingly. So then the second bit brings us from single Rydberg excitations of ions to many body effects. We talk about structural phase transitions, linking also to work of Giovanna Morigi, for instance. She's not here, and also to something also Tobias pointed out in his Outlook slide. We talk about Rydberg excitation of a linear crystal, then also vibrational mode shaping. You will see what that means later. Motional quantum gates based on Rydberg excitations, also phase transitions in open system settings that you can explore. And finally, and actually this is the real reason why I kind of had to come up with this sort of clunky title, because finally we move away from ions to atoms, and I will show you that we can also use those Vibronic couplings in the context of neutral atoms to do some interesting stuff, based on state-dependent forces, which are, of course, a very popular tool in the context of trapped ions, but you will see also, in principle, this works in the situation where we have neutral atoms and tweezers, will give rise to effective three-body interactions, and then we can do some interesting many-body phase structure studies in these systems as well. Okay, so trapped Rydberg ions. So, I don't know, I'm having the constant feeling that I'm somehow blocking the view here, so you tell me. And also, this is kind of intimidatingly close. This is the second reason. So, trapped Rydberg ions, so what's the story in a nutshell? Basically, this is what it is, right? So we have here our ion crystal, so we want to pull apart an electron and this twofold charged core, and then of course exploit somehow the interaction between the dipoles, the dipole moments that we create within those Rydberg ions. So, and why would one want to do that? Actually, I had to revise the slide a bit because it was devised here 10 years ago, before all these kind of Rydberg tweezer arrays were popular. So what I wrote here, instead of trapped localized qubits, I wrote extremely long-lived trapped localized qubits. So maybe this is the distinct advantage. Still, near unity detection efficiency of trapped ions, We have a very reliable state tomography with capabilities that are still better, I would say, than what is available for Rydbergs and tweezers. And we have, of course, quantum gate operations, and I put here this X. I don't know what the state of the art is right now, so how many nines we have here for 2 qubit gates. You might have mentioned this, so in the talk, I don't know. Did you? Is it 3 nines?
So it's 9x now, right?
And now, why Rydberg interactions? Of course, okay, what we want to do is we want to do somehow blockade physics, hopefully, and I will convince you, hopefully, that this is bringing some new aspects into the game here. We will have long-range interactions in quotes, because, of course, in ion traps we have got long-range interactions due to the exchange of phonons. We have fast gate operations that are independent of vibrational modes, and this is, so to say, what the real deal is here, and Marcus is going to talk about this aspect to a great extent, I guess, on this morning. So I avoid talking about this at all, more or less here. So now the challenges, and of course I'm sort of a neutral Rydberg guy owed to my upbringing, so I used to deal with atoms that are found in the first group of the periodic table. They have a simple level structure. Same is of course true if you take those atoms in the second group of the periodic table and strip away one electron, then this also looks pretty much like hydrogen, and we know the level structure looks like this. So we have here the grouping of these excited Rydberg states into multiples that are labeled by the principal quantum number n. But the difference here now is that this Z, which is the nuclear charge, is no longer 1, as it is the case for the hydrogen-like atoms, but it's actually 2. And of course, it's a trivial fact, but it has implications. For instance, it will reduce the interaction strength between excited Rydberg states because the corresponding dipole moments will become smaller. Okay, now I'm a theorist, I have to say, so take this with a grain of salt. So what are the challenges? Well, experimental challenge is clear. Yeah, so I mean, you need to excite those things. And for me, there's no difference whether this is a neutral Rydberg atom or a Rydberg ion. So what I understand, it's a bit more problematic for the ions. And then for the theory side, you see this is kind of Brexit speech. Yeah, what's the challenge? No, it's not a challenge, it's an opportunity. Yeah. So I hope the joke is not lost on you. To understand the spectrum, of course, to understand whether these objects are stable, and also finally to understand how they interact and what opportunities may emerge. So there are two candidate systems in which Rydberg excitations are attempted, and I think, well, in the context of aiming at kind of quantum simulation computation, of course. Spectroscopy existed before that. One is calcium-40, where the plan was in Ferdinand Schmidt-Carlos and Jochen Weil's group to excite ions from the D state directly with a single photon to high-lying Rydberg states, CF states. And you see, I mean, it's a rather unpleasant wavelength here of 120 nanometers, which you generate in this particular case by 4-wave mixing within a mercury vapor cell. And well, this is what I took away from that. So pretty pictures. So lots of colors brought together in the cell, and then out comes this difficult to handle vacuum ultraviolet laser beam. But it worked, and you will see first results were published actually in 2015. So, but then Marcus came along, and you will tell the story in a much nicer way, and said, well, why put up with this? Just go from the D states of strontium to the Rydberg states with a 2-photon transition, which turns out not to need an entire room full of an experiment in its own right, just to generate the laser, but to be something that can be actually set up in a reasonably straightforward way. And this is also the one that has given very nice results that Marcus is going to talk about on Wednesday. Okay, so this is as much as I want to say about experiments, so let's come back to the interesting theory questions that immediately emerge, and just to say what has been said already a few times today. well, when we want to trap ions, we need electric fields, and you see here it's written down the potential of a Paul trap, and you see it's composed of an oscillating part and a static part, and we of course know that there are regimes of stability where this time-dependent potential gives rise to an effective harmonic static confinement, and we can very nicely model ions, point-like ions, as if they were particles in a harmonic trap with some actual and transverse frequency that depends on those RF field gradient here before in front of the oscillating term and the static field gradient beta in front of the static term. Fine, so far so good. Now let's think about length scales and ions and Rydberg states of ions, and then if you wanted to draw a picture, you would draw something like that. Yeah, so some positively charged core encircled by an electron, and typical distance here in the order of 100 nanometers, which is, just look it up, corresponding to a dipole moment of about 5 kDi. So huge objects that carry a strong dipole moment. And now if you just compare this with the length scale of typically trapped ions experiments, you will find the following. Yeah? So the interparticle distance here is roughly 5 micrometers, the harmonic oscillator length is roughly 10 nanometers. So you really see that this Rydberg radius extends far beyond the oscillator length corresponding to the harmonic local confinement of each ion. So it's a nice regime, but you might ask, well, surely this ion trap is not such a harmless harmonic potential, but it's really composed of strong, in quotes, static and time-dependent electric fields, and you might wonder, well, is this whole object stable in such a kind of harsh environment? Because these electric fields, of course, try to tear the positively charged core and the electron apart. And then you can do a very simple calculation just to estimate, as one would do for neutral atoms in the presence of an electric field, whereas the saddle point of this Coulomb potential that is bent down by the imposed electric fields, and you see that then for moderate or for typical experimental environments, one should be safe up to principal quantum numbers on the order of 50 to 70, which is compatible with what is actually observed in the experiment. So these things are stable. Of course, you cannot go to excessively large principal quantum numbers like neutrals. You can go up to, I don't know, 300 or even higher. This is certainly not possible in this case here. But then there's one interesting aspect here, which I also sort of started conveying by plotting this picture where we compared the length scales, namely that a Rydberg ion is not a point particle anymore. Right? This is really an important message to bring across. You really have to take into account that the electron and the positively charged nucleus couple separately to the electric field that surrounds them. And again, here's the electric field of the Paul trap. And of course, you can now write down the entire Hamiltonian of the system. To make a long story short, I just want to show you that there is a term that emerges when you do this calculation, that indeed you see this immediately couples the center of mass motion corresponding to the capital letters to the electronic motion, which is here represented by the lowercase letters. So internal and external motion are no longer separable, and this gives rise to these Vibronic couplings and actually underlies a number of very interesting effects that I'm going to talk about now. One effect, and this is a rather simple one, is that actually the electronic levels are shifted, clear, but then also the next level of complexity, one finds also that the confinement is actually altered. That in general, of course this is no news if you consider any trapped object, even neutral atom, one finds that the ground state shows a different confinement potential than, for instance, a Rydberg state of an ion. And the trap frequency is actually modified by a factor that is proportional to the lowest order to the polarizability of the state. Also no news, but it's actually giving rise to very pronounced effects that are much more dramatic than they are, let's say, in the context of neutral atoms. So just one thing one can probe here, and this is really just the one experimental result that I stole from you, Marcus. So maybe you can replace the slide. No. Is that you can actually measure this, right? And when you, for instance, at the situation in strontium, you have here the confinement potential for the ground state, so the electron surface. If you think of a molecule of the electronic ground state, and you have a higher excited electron surface, then you see, due to the slight change of polarizability of the excited state, the Rydberg state with respect to the ground state, you get also shifts of the oscillator states here. Yeah? And you see that with respect to the unperturbed oscillator, you see there's this deviation which then grows linear with a population number here. Yeah? Delta omega, 2 delta omega, and so on and so forth. And this you can measure with an experiment that prepares these Fock states and then the spectroscopy and, so to say, maps out this energy shift. And indeed, as shown by Marcus and this group in a very recent paper, you see that there's this linear shift on the resonance condition, which really is reproducing this picture that I plotted here on the left-hand side. So the extremely nice thing is that this can be tuned, but this is something Marcus is going to talk about. So, okay, this was a single line, yeah, and of course, maybe no surprises in the sense that well, the potential that one finds in the end is depending on the internal state of the ion. But now let's go away from this single body picture and look at many body effects. And here it becomes interesting. And just to make the point, I start by a very simple setting where we just focus on a crystal composed of 3 ions. And now you know, if I increase the confinement, the actual confinement, at some point there will be a phase transition. Also, we showed some nice pictures in Chris, I think, showed a picture was in the stock, and you mentioned it in the outlook. If you increase the confinement, what will happen is that this 3-ion crystal will undergo, in quotes, a phase transition from a linear to a zigzag configuration. So, and this transition takes place at a critical gradient, beta, doesn't matter, so it's some number. And but what we also know is that if we now want to excite an ion from its ground state to the Rydberg state, we also alter the local confinement of the Rydberg state due to the difference in polarizability with respect to the ground state. So, and this additional confinement, as I said, depends on the polarization and hence also on the principal quantum number. So there should be, in fact, an n-dependent, so a gradient, meaning, okay, a gradient, a critical gradient for this linear to zigzag transition that depends on the principal quantum number. And this indeed tells us that the equilibrium configuration of the crystal, meaning whether it's linear or zigzag, depends on the field gradient, of course, but also on whether the ion in the middle is excited to the Rydberg state or not. And now we can draw this kind of phase diagram as you wish, and you can plot here the gradient, and here you plot the principal quantum number. And what you see now is that, let's start with this bottom bit here. You see now that if I cross with my gradient this line, this crystal which is composed of 3 ground state ions becomes zigzag crystal composed of 3 ground state ions, and the same would hold if if I now didn't have a ground state ion but instead a Rydberg ion in the center. You see, okay, this line, crossing this line does not lead to a phase transition, but instead there's a second line here crossing which would now promote this linear crystal into a zigzag crystal. Yeah, and indeed, as predicted, okay, by theory, confirmed by theory, so there is this independent boundary. And of course, this is in principle something that one could measure, that the critical gradient, of course, for ground state ion does not depend, nothing. That there is a critical gradient for the Rydberg ion that depends on the degree of the excitation. And also related work, and I think also this is something Tobias mentioned, is of course done in the group of Giovanna Modici. Good. So what does it mean in practice? So this means now that in fact, even the excitation of a single ion within an ion crystal is a many-body effect, right? Because if you happen to be close to this kind of phase transition, then if you wanted to excite this Rydberg state of the central ion, you would have to change, in fact, the structure of the crystal if you wanted to stay in the ground state. And indeed, if I wanted to plot it in terms of some kind of potential surfaces reminiscent of molecules, you would probably do it like that, right? So where you have here your ground state, let's say it's the other way around now, zigzag configuration, which then becomes a linear crystal if you excite the Rydberg ion in this situation. You see, we would plot this by two displaced parabolas with also different trap frequency. And now if you were to look at the laser excitation, you would see immediately that also there in the spectroscopy, you would find that due to the displacement and the change of shape of these potentials, non-trivial Franck-Condon factors would appear, which are no longer delta functions, but you would be able really to excite from the ground state of the lowest potential surface, also highly excited state of the upper potential surface. Yeah. So something like this should be observable in the experiment, and okay, I'm looking forward to corresponding results. So what else can one do? Yeah. One other thing one can now exploit is that in some sense these Rydberg atoms, or these Rydberg states, are allowing you to kind of dynamically chop an ion crystal. And if you, for instance, take a long crystal here, I think Chris, this is one of your papers, if I'm not mistaken, I don't know. I think so. You might not remember. Where one looks at a linear or close to linear ion crystal, so in a kind of not a parabolic trap, one finds in this situation that the mode spectrum looks like this, where we have here the number of ions and here the index of the mode. So, okay, looks like something. So it's definitely complicated, and all ions contribute to all modes, more or less, yeah, except here for the bottom. So now, if one wanted to kind of bring some order into this chaos of modes, what one could do is one could try to excite Rydberg atoms or Rydberg states of ions at certain positions, right? And thereby isolate kind of substrings from the rest. Yeah, and you see this very nicely here. Yeah, so this is kind of a crystal that is being chopped apart by those two Rydberg excitations. You see here very nicely these isolated modes, which also are very separate, unlike the quasi-continuum of the other modes spectroscopically. This would provide you with the means to dynamically resolve these modes and even disconnect certain parts of the ion crystal to perform gate or measurement operations in parallel without affecting the rest. So this is one idea that one can pursue with these Rydberg excitations. Another thing, and you see I'm just kind of flashing the possibilities, so it's not really possible to talk about everything in great detail. Another thing one can do is one can exploit the large forces that come with the fact that one excites those ions to Rydberg states. This is an idea we have explored very recently with Ferdinand's group in Mainz. And what you can do is you can basically follow these geometric gate ideas that are around since quite some time already, where you push ions with state-dependent forces. Okay, shouldn't have told the referee maybe. So the referee liked it, we like it a lot. Yeah, but at the end of the day, it's kind of a different manifestation of these push gates, where you have state-dependent forces, but the theory is a bit more involved, because you not only push your ground state with respect to the Rydberg state, but you also change the shape of the potential. So what you can do here is you can now apply an electric field to your system that is composed of an ion which can be in a superposition between the ground state and the Rydberg state, and the Rydberg state will respond to the electric field differently than the ground state. Now you employ an electric field, you kick the ion, and if you do this in the right way, you manage in phase space to close the trajectory. So you basically make the final state look like the initial state, apart from the fact that you get a phase out. In this geometric phase, it allows you to not only perform kind of a gate operation on a single ion, but you can also do the calculation for more ions, and you find very nicely that indeed you can pick up an entangling phase with a fidelity which is essentially limited just by the lifetimes of the ions, and on a time scale which is pretty fast. Yeah, so here 0.05, let's say, to be optimistic, microseconds. So this is really nice because it allows you to exert, this Rydberg excitation allows you to exert extremely strong forces by electric field kicks, which allow you to accumulate phase in a very short amount of time, and then gives rise to these kind of entangling operations. All right, and the last thing that I wanted to say about the Rydberg ions is also now that you can go away from these settings where we look at completely closed quantum dynamics, which is fully coherent. What we can also do is now we can take an ion system which we drive with a laser, and to Rydberg states, and then we of course know that these Rydberg states decay. So in the ideal world, we model everything by two-level systems. We can also monitor the fluorescence of these ions. And what we can then do, at least in theory, is to infer by monitoring the fluorescence of those ions, of this ion system, what kind of phases this coupled system, this open quantum system, can assume. So how does this work? Also very briefly, you can now write down a Hamiltonian for the system. Of course, I'm only covering the coherent part here. And there you see, well, this is the laser excitation here. This is the long-range interaction between Rydberg states. And then in addition here, you have this Vibronic coupling, this coupling between the phonons and the spins. And one part here is kind of the standard state-dependent force that you get when you have ions in the standing wave. But then here the second part is due to the fact that the trap frequency of the Rydberg ions is different in comparison to the trap frequency of the ground state ions, and this gives rise to this coupling term. So, and now what you can do, you just put in the decoherence mechanism, which is just radiative decay. You write down a master equation, and you try to find the stationary state, and in the stationary state you calculate, for instance, the photon fluorescence, and you can count the number of photons per time. You can form a histogram. You can count the moments, whatever. So, but what's very nice, and unfortunately I don't really have the time to talk about this in very great detail, but this is super lovely. Just you can map out phase diagram here, and you find phases. Just don't look at this; it's awful. I know. You get something like phonon lasing. You get Dicke physics. You get also Dicke model physics. You get critical points, and all these features have kind of a signature. All these phases have a signature that you, in principle, can detect by performing proper statistics on this photon count here. And so, not only that, but in principle, if you can also, which is of course less straightforward, because photons here come for free, provided that you can detect them well. But of course, these phases also have a correspondence in the spin state that is assumed by the ions, and you have kind of this duality between the spin state of the ions and the photon emission statistics that you get as the output of the system. So, can only encourage you, maybe just to look at this paper, but rather to look at the references here, because I think this is a fantastic playing field also for trapped ion experiments. Just looking what the fate of these systems do in an open setting, where you look at the output and then try to analyze what the output does as a function of the system parameters. So I think it's really nice physics. Perfect. Okay, so this brings me also kind of towards the end of the talk, where we will be leaving the notion of Rydberg ions and come back to neutral Rydbergs. And what I want to talk about is something that is very much related. Also, Alexei is not listening, it's a pity, but I'm just citing you here. Recent work of yours, which is related to some of your recent works, where you're also looking at the coupling between vibrations and Rydberg excitations. So just how does the story go? Well, we have again an atom, which is an optical tweezer, let's say. We have harmonic confinement. This atom is forming, in the ideal world of the theorist, a two-level system, which looks like that. And you can write down now, of course, the Hamiltonian, where you just assume, and this is, of course, counter to what I just tried to advertise in the first part of the talk, that you have this difference between the trapping potentials, where I just assume that the trapping potential between for the ground state is the same as for the trapping for the Rydberg state. So you can write down the Hamiltonian for the phonons and an atom-laser interaction, and both are generally non-coupled, right? So you can do with the phonon state whatever, or with the electronic state whatever, and both don't see each other. So now, this is of course not what I'm interested in, but what I'm interested in now is to look at the same situation, but for two atoms. And there, of course, we obtain a coupling between the internal and external degrees of freedom simply due to the fact that when I excite two atoms to the Rydberg state at the same time, there's of course an energy shift, but there's also a force, which is due to the gradient of the potential. And as per this picture, you see that atoms in the doubly excited state experience also this Vibronic coupling, very much like what I advertised for the Rydberg ions. And this can actually be employed for mediating non-binary interactions between Rydberg atoms. And how to see how that works, we just look at the interaction potential between two atoms. So, and I will draw an analogy very quickly to the state-dependent forces that one normally uses, for instance, to generate spin models in your trapped ions. You will see the physics is exactly the same. So what you do have in general is kind of a potential, two-body potential, and this is multiplied by the projectors on the Rydberg state of the atom 1 and atom 2. So only when both atoms are excited, they feel this potential. But now, of course, I can expand this, and usually what one does is one just takes the potential at the equilibrium position of the atoms and gets here a number times this projector. But now, of course, one can do the expansion one step further, and one sees also that one now couples to the bosons. Makes sense, right? Because in the next order you get this displacements in, and you get a spin-spin interaction in the leading order. In the next order you get this electron-phonon interaction, which is exactly this mechanism that displaces your trapping potential when both atoms are excited at the same time. Good. So, and again, you've been talking about exactly the same thing now, but in the single ion context where you have a standing wave, and you see here you have the gradient of your electric field, of the intensity, going across this ion. You expand this around this ion position, and typically what you get is you have the phonons, and yet you get this state-dependent force. This is what we write down, and we know, okay, if we now integrate out the phonons, we've seen this also this morning in Chris's talk, we get an effective Ising Hamiltonian here, sigma z, with some prefactors that you can tune, and you can make it long range, short range, as you wish. The same thing works here, and I want to spare you the math, so you can do exactly the same procedure now for the situation where we look at this doubly excited state. And what you get in the end is that you get a Hamiltonian. Just look at me, don't look at this. I don't know what's more pleasant, but again, so you get a Hamiltonian that depends on two body terms, nk and m, and you get a part that depends on the state of three atoms at the same time. So two body for potential and a three body potential. And you can now, on the square lattice or honeycomb lattice or any lattice you wish, analyze what is the shape of these two body and three body potentials. So you see, for instance, this is maybe most interesting here, that those are the simplest case, those for a square lattice are the leading contributions here, two-body interaction here, two-body interaction along the diagonal. These effective interactions create the new interactions here along this, along nearest neighbors, up, down, and left, right, but also the three-body interactions here across those horizontal or vertical lines. The interesting thing is now that these two-body interactions that emerge here effectively can cancel the two-body interactions that are actually present naturally in this system. So that in leading order, if you do it right, you get actually three-body interactions. This is kind of cool. So why three-body interactions? Well, just to see why this makes sense. Because we have actually, if we wanted to understand what's the force on this red ion, we have to understand what is the state of the atom to its left and to its right. And you see, when both atoms to the left and the right are not excited, then there's of course no force acting on the center. And also, if both atoms to the left and the right are excited, then there's also no net force on this atom in the center. So that makes sense. In order to describe something like this, we need three body forces. And just to bring the talk to an end, now what you can do is you can, of course, this is the simplest calculation you can do. It actually turns out not to be too simple. So it's for 2D 10 by 10 square lattice, where you just plot here in the y-axis the three body interactions, and here in the x-axis the binary interactions, and then you see for kind of three different order parameters what the phase diagram looks. So this is just the density of excitations. This is the density of dimers, so atoms that are in the Rydberg state are next to each other, and trimers, so basically triplets of atoms. And you can associate a number of phases and phase transitions, and you see just here some examples. So this is the simple one, the checkerboard. So then you get striped phases, you get striped phases, what we call frustrated. I mean, in the end, it's a finite size effect because you just are not able to fit enough stripes in here. But then also you're able to transition to some kind of clusters where these three body forces force you basically, or tell you that it's energetically favorable to form these quadruplets of atoms that are effectively bound together. So this is just a start, and we continue playing with that, but I think if this really worked, that would be actually quite nice. Good. Okay, so this brings me to the summary. What did I tell you? I hope I could convince you that this notion vibronic coupling somehow makes sense in the context of Rydberg atoms and Rydberg ions. Showed you that even for a single Rydberg ion, the laser excitation might be a general many-body effect, because you have to essentially take the entire crystal with you if you happen to be at a kind of sensitive point. The strong forces that one can generate are useful for quantum gates. There's very vaguely, I presented this a possibility to study many-body open system dynamics, and I showed you at the end that actually also similar physics applies in the context of Rydberg atoms and optical tweezers, where you can, due to this vibronic coupling, get effective three-body interactions. Marcus will do the real deal on Wednesday, so with real experimental data, and it's so nice, so just stay tuned. It's super cool, in my opinion. So where to go from here? Well, of course, now you can do a number of things. You can go away from this kind of coherent picture of these interactions. You can do some kind of path engineering with the phonons. You can look at local versus non-local phonons, because this whole kind of analysis that I just made for the optical tweezers, you can of course do also for the trap, and you get some kind of three-body forces which are longer range and not restricted to nearest neighbors or next nearest neighbors. And one would wonder if it's possible, but I have my doubts, to actually engineer the n-body forces that go beyond 3. Nice to see. There's other stuff that's going on, from fashionable topics to others, like dressed dense atomic gases, all kind of quantum generalizations of neural networks that we are currently pursuing. If you're interested in those, please have a look at those publications. Thanks a lot for your patience. I'll give back to the channel.
We have time for a couple of brief questions.
Yeah, I have maybe a dumb one. So can you say again how the three-body interactions come about? Because if you're coupling to a bosonic field, it has to be more than just that, right?
Well, look, I mean, I tell you how. It's very, I think you see it already in this slide. Here, we have both. In the ions, when you have the state-dependent force, right, you have for a single ion, you have this fundamental starting point here. So bosons times a single operator in the spin. When you integrate out the bosons, this sigma z is kind of squared, in a stupid way, and then you get a sigma z.
So you don't have any more boson terms, then? It's just...
No, but it gets squared, and then it's this icing model, and the bosons are gone.
Okay.
But here you see our starting point is a different one, so we do not start with one sigma z operator, but we effectively start with 2, right? And then we square those,
I got it.
and you see the dominant contributions from the three-body part.
Okay, thanks.
So I don't have a feel for what the strength of these vibronic couplings, as you're calling it, versus the direct dipole-dipole interaction. Is this much weaker? Is it the same strength?
In the context of the neutral atoms in this...
Well, let's start with the neutral atoms.
Well, at least I can give you an answer.
Okay.
So, as I said, the funny thing is now that if you start from because this is general, right? I mean, there's some ugly-looking expressions which depend on the nearest neighbor, next nearest neighbor potential. Now, when you assume that you can tune the potential and the gradient of the potential at nearest neighbor distance independently, which is possible, for instance, through dressing microwave fields, putting two potential surfaces together. I didn't say all this, thanks for asking. Then you can really get a situation where this effective two-body potential that you generate through the coupling to the bosons has the same strength, but with opposite sign, as the fundamental dipole-dipole interaction. And both can cancel. And then the leading order is actually this three-body term. At least the theorem says.
I'll take your word.
Yeah, well, you can. There is even a paper. Yeah, you can look it up in the paper and the numbers.
So the way you get three-body terms is by starting from dipole-dipole interactions, and
Correct.
giving two-body terms, and
Yes.
then integrating over motion, which results
Correct.
in order.
Yes.
But I mean, with these Rydbergs, if the Rydberg radius becomes comparable, or I mean, there is another correction which would give you three-body terms directly. Is that true? I mean, just if for example, if the Rydberg radius, going the trajectory of the electron, becomes comparable to the separation between atoms, then already the dipole-dipole would be an approximation. The higher order term would be three-body directly.
Is it really that it's three-body interactions, but not rather quadrupole terms? I mean, there's a whole mix, right? In the end, what you're just saying is you have to diagonalize the matrix, which I happen to be able to diagonalize by perturbation theory in this regime.
Yeah.
This is not valid anymore. Anything happens. I get in other words, very complicated energy surfaces that I cannot just any longer expand by sums of binary interactions. That is correct, yes. But we are far away from this regime.
Also related to that, like, do you need to have a zero temperature here for your atoms, or because you're mediating your interactions with the...
That is a good point.
It's really high.
And the underlying assumption here is that indeed you are in the ground state, and of course, normally I'm giving the talk in a different way. Normally the first part is about disorder due to the different temperature-dependent position. Due to the shot-to-shot differences of the positions of the atoms in the tweezers, right? And then this is the part where I say, okay, if we were able to cool this down to the ground state, this is the physics you'd see there. Interesting would, of course, be how do you interpolate between this?
Okay, so that's like for the first part, so you should probably adjust that, but as far as I understand, probably why actually the single Rydberg ionization works is because the equilibrium you're setting at the field.
Correct, yes.
Otherwise you have enormous fields.
That is absolutely correct. This is the reason, right? It's a gradient field.
But now I was wondering if you now do these transitions between the zigzag and the line, for example, where you probably excite like highly off.
Yeah, you're right.
State, or you do your kicks. Don't you kill the Rydberg state?
Well, not necessarily. I mean, there's a whole part of the story which I didn't show, right? Because you can do some kind of serious atomic physics there in the presence of these inhomogeneous trapping fields, and you will see that, okay, you get all sorts of mixing between magnetic substates and so on. So it's very complicated. You get, okay.
So it's only true.
It's in this proposal for that I just showed you. It's not included because, okay, we wanted to go for the effect in the paper, but we know what to do. I mean, we have the theory, and it's also published for single Rydberg excitation in the environment of this approach. Of course, this would now have to be done properly also for those three ions. Yes.
Okay, then let's thank you both.